The halls of NASA headquarters have witnessed countless announcements over the decades, but few carry the weight and urgency of what theoretical physicist Michio Kaku recently described as humanity's most critical crossroads. In a series of interviews and public appearances throughout 2024 and into 2025, Kaku has been sharing insights about NASA's latest findings that paint a picture both exhilarating and sobering about our future among the stars. The renowned physicist, known for his ability to translate complex scientific concepts into language that captures the imagination, has become an unexpected voice of both caution and inspiration as space agencies around the world grapple with challenges that previous generations could barely imagine. What makes Kaku's perspective particularly compelling is his unique position straddling the worlds of theoretical physics, practical engineering, and public communication. He understands not just the mathematics of space exploration, but also the human element, the dreams and fears that drive us to look upward even as we struggle with problems here on Earth. His recent discussions of NASA's findings reveal an agency at a turning point, armed with unprecedented data from new missions, yet facing obstacles that test the very limits of human ingenuity and determination. The James Webb Telescope revelations. When the James Webb Space Telescope finally launched in December 2021, after decades of development and numerous delays, it represented not just a triumph of engineering, but a new window into the universe's deepest mysteries. Michio Kaku has described Webb's early findings as simultaneously confirming and challenging our understanding of cosmic evolution, revealing a universe more complex and surprising than even the most optimistic astronomers had predicted. The latest data from Webb has focused attention on the earliest galaxies, structures that formed in the first few 100 million years after the Big Bang. According to previous models, these early galaxies should have been relatively small and disorganized, slowly growing over billions of years into the massive spiral and elliptical galaxies we see in the nearby universe. Instead, Webb has discovered surprisingly large and mature galaxies existing at times when such structures should not have been possible according to our standard models. Kaku explains that these observations do not overturn our fundamental understanding of the universe, but they do require adjustments to theories about how quickly structures formed in the early cosmos. Perhaps dark matter clumped together more efficiently than we thought, providing gravitational seeds that allowed normal matter to collect and form stars more rapidly. Or perhaps our estimates of how quickly stars could form in the extreme conditions of the early universe were too conservative. What makes these findings particularly relevant to NASA's exploration goals is what they reveal about planetary formation and the potential prevalence of habitable worlds throughout the universe. Webb has begun characterizing the atmospheres of exoplanets, worlds orbiting other stars, with unprecedented precision. By analyzing the light from distant stars as it filters through these planetary atmospheres, scientists can identify specific molecules present in the alien air. The latest NASA findings include detections of water vapor, carbon dioxide, and other molecules essential for life as we know it on multiple exoplanets. Some of these worlds orbit in their star's habitable zone, the region where temperatures could allow liquid water to exist on the surface. While none of the characterized planets so far are truly Earth-like, the data suggests that worlds with conditions suitable for life might be relatively common throughout our galaxy. Kaku emphasizes the philosophical implications of these discoveries. If habitable worlds are common, then the question of whether life exists elsewhere becomes not if, but where and when. The universe revealed by Webb is vast beyond human comprehension, containing hundreds of billions of galaxies each with hundreds of billions of stars. Even if life is relatively rare, the sheer number of potential habitable worlds means that Earth is almost certainly not unique. These revelations inform NASA's long-term planning in subtle but important ways. If life is common, then contamination protocols become even more critical. We must ensure that Earth microbes do not hitch rides on our spacecraft to Mars or Europa or Enceladus, potentially destroying alien ecosystems before we even discover they exist. And if technological civilizations are possible elsewhere, then our signals leaking into space, both intentional and unintentional, become messages in bottles cast into a cosmic ocean that might not be as empty as we once thought. The physics of faster space travel. Perhaps no topic excites Michio Kaku more than the possibilities and challenges of advanced propulsion systems that might someday allow humans to travel between stars. In discussing NASA's latest research into propulsion physics, Kaku brings together his expertise in theoretical physics and his understanding of practical engineering to paint a picture of both near-term possibilities and far-future dreams. Current space travel relies on chemical rockets, essentially controlled explosions that push spacecraft in the opposite direction. These systems are mature, reliable, and fundamentally limited by the amount of energy that can be extracted from chemical bonds between atoms. NASA's latest findings include research into ion propulsion systems that use electricity to accelerate charged particles to extremely high speeds. While these systems produce tiny amounts of thrust compared to chemical rockets, they can operate continuously for months or years, eventually achieving speeds that chemical rockets could never match. The Dawn mission, which explored the asteroids Vesta and Ceres using ion propulsion, demonstrated the technology's potential. But Kaku points out that even ion drives, operating at their theoretical limits, would require centuries to reach even the nearest stars. For true interstellar travel, we need breakthroughs that go beyond refinements of existing technology. Nuclear propulsion represents one possible path forward. NASA has been quietly advancing research into nuclear thermal and nuclear electric propulsion systems that could dramatically reduce travel times within our solar system. These systems use nuclear reactors to heat propellant to extreme temperatures or to generate electricity for powerful ion drives. The latest findings suggest that nuclear propulsion could cut Mars travel time from months to weeks, reducing radiation exposure and opening possibilities for more ambitious missions deeper into the solar system. But Kaku emphasizes that nuclear propulsion, while revolutionary compared to chemical rockets, still falls far short of what would be needed for practical interstellar travel. He discusses more speculative concepts that NASA and other agencies are studying at theoretical levels. Antimatter propulsion, which would harness the complete conversion of matter to energy when particles meet their antimatter counterparts, could provide energy densities millions of times greater than chemical reactions. The challenge is that producing and storing antimatter requires enormous amounts of energy and technology we have not yet developed. Even more exotic are concepts involving warping space itself, creating shortcuts through the fabric of the universe that might allow effective faster-than-light travel without violating the cosmic speed limit. Kaku, an expert in string theory and theoretical physics, explains that while such ideas are consistent with general relativity under certain highly speculative conditions, they require forms of exotic matter with negative energy that might not exist in our universe. And even if they do exist, we have no idea how to produce or control them. The latest NASA research focuses on more modest but still revolutionary concepts: solar sails that use light pressure from the sun for propulsion, laser propulsion systems where powerful Earth-based lasers push ultra-lightweight spacecraft to relativistic speeds, and fusion propulsion that would harness the same nuclear reactions that power stars. Each approach faces enormous technical challenges, but unlike warp drives and wormholes, these concepts do not require new physics, only extraordinary engineering. Kaku stresses that developing advanced propulsion is not just about satisfying human curiosity to explore distant stars. Even modest improvements in propulsion efficiency would revolutionize exploration of our own solar system, making missions to the outer planets routine rather than decades-long endeavors that few spacecraft attempt. The Voyager probes launched in 1977 are only now leaving the solar system's immediate neighborhood after more than 40 years of travel. Faster propulsion would mean shorter missions, reduced costs, and the ability to explore multiple targets during a single human career rather than requiring generational commitments. The economic realities and the cost of dreams. Michio Kaku often reminds audiences that the greatest barrier to space exploration is not physics, but economics. NASA's latest findings include not just scientific discoveries and technical achievements, but also sobering analyses of the costs involved in ambitious space programs and the political challenges of sustaining funding over the decades required to achieve transformational goals. The Apollo program, often held up as an example of what determined commitment can achieve, consumed more than 4% of the entire federal budget at its peak. The United States spent roughly $280 billion in modern currency to land 12 people on the moon over a 3-year period. That level of spending was possible because of unique political circumstances, Cold War competition with the Soviet Union, and a desire to demonstrate technological superiority that no longer drives space policy in the same way. Today, NASA's budget represents less than 0.5% of federal spending, and the agency must balance multiple competing priorities, including Earth observation, climate monitoring, aeronautics research, and space exploration. The Artemis program's costs have been estimated at $93 billion through 2025, substantial but modest compared to Apollo when adjusted for inflation and economic scale. Kaku points out that critics who call space exploration wasteful spending often fail to consider both the tangible returns and the inspirational value of pushing human boundaries. The latest economic analyses show that space exploration generates returns through technology transfer, with innovations developed for space-finding applications in medicine, communications, materials science, and countless other fields. GPS satellites that enable modern logistics and communications, weather monitoring systems that save lives by predicting hurricanes and other disasters, satellite communications that connect remote regions to the global economy. All these capabilities emerge from space programs that critics dismissed as expensive distractions. But Kaku also acknowledges that the pure exploration component, sending humans and robots to distant worlds simply to learn and explore, requires justification beyond economic returns. Here he emphasizes the inspirational and educational value, the way space achievements excite young people about science and engineering, creating the next generation of researchers and innovators who will tackle challenges both in space and on Earth. NASA's latest findings include data on public engagement and the impact of missions on educational interest. The Perseverance rover's landing on Mars in 2021 was watched by tens of millions of people worldwide. Images from the James Webb Space Telescope routinely go viral on social media, reaching audiences far beyond the traditional science enthusiast community. These engagement metrics suggest that space exploration, even in an age of pressing terrestrial concerns, still captures human imagination in ways few other endeavors can match. The challenge is translating that enthusiasm into sustained political support for funding. Kaku notes that space programs operate on timescales measured in decades, while political cycles operate on timescales of years. A president who launches an ambitious space initiative will likely be out of office before major results become visible, reducing the political incentive to commit to truly long-term goals. The latest NASA strategic planning documents attempt to address this challenge by breaking large goals into smaller milestones that provide visible progress and maintain public interest. The Artemis program's approach of first flying uncrewed tests, then crewed missions around the moon, then lunar landings, and finally sustainable presence represents an attempt to show continued progress while building toward the ultimate goal, the question of why we explore. In his most philosophical moments, Michio Kaku addresses the fundamental question that underlies all discussions of space exploration challenges. Why do we reach for the stars when problems persist here on Earth? Why spend billions exploring Mars when people suffer from poverty, disease, and injustice on our home planet? The latest findings from NASA and other space agencies provide data and discoveries, but they cannot answer these deeper questions about human priorities and values. Kaku's response draws from both scientific understanding and humanistic reflection. We explore, he argues, because it is fundamental to what makes us human. Every major advance in human civilization has come from pushing boundaries, from investigating what lies beyond the next hill or across the next ocean. The same curiosity that drove ancient humans out of Africa to populate the globe now drives us upward into space. But beyond philosophical arguments about human nature, there are practical reasons why space exploration deserves priority even in a world facing serious challenges. Climate change, perhaps the greatest threat facing humanity, is better understood through space-based observations than any other method. Satellites monitoring Earth's atmosphere, oceans, and ice caps provide data essential for understanding and addressing environmental changes. The same technologies developed for sustaining life in the harsh environment of space have applications in developing sustainable systems on Earth. Asteroid mining, still speculative but increasingly within reach technologically, could provide access to mineral resources worth quadrillions of dollars while reducing the environmental impact of terrestrial mining. Solar power satellites that collect energy in space where the sun shines constantly and beam it to Earth could provide clean, unlimited energy for human civilization. These practical benefits from space development could help solve terrestrial problems rather than distracting from them. Kaku also emphasizes the long-term perspective. Humanity will not survive indefinitely on a single planet. Whether the threat comes from asteroid impacts, climate catastrophe, nuclear war, or threats we cannot yet imagine, keeping all humans on Earth means accepting that our entire species could be extinguished by a single catastrophic event. Becoming a multi-planetary species, establishing sustainable presence beyond Earth, is ultimately about survival. The latest NASA findings contribute to this long-term vision by revealing what challenges must be overcome and what opportunities exist among the worlds of our solar system and beyond. Each discovery about radiation on Mars or water ice on the Moon or the composition of distant asteroids informs our understanding of how humans can eventually establish themselves throughout the solar system. The road ahead and humanity's choice. As Michio Kaku surveys the landscape of NASA's latest findings and the challenges they reveal, he returns repeatedly to themes of choice and determination. The barriers to space exploration are real and significant, from radiation exposure to vast distances to economic constraints. But none of these challenges are fundamentally insurmountable. They require commitment, resources, international cooperation, and most importantly, sustained effort over decades. The next few years will prove critical in determining whether humanity's current push into space represents a genuine turning point or just another false start. The Artemis program must deliver on its promises to establish credible momentum. International cooperation must expand rather than fragmenting into competing national programs. Private space companies must mature from promising startups to reliable partners in exploration. And public enthusiasm must translate into political support for continued funding. Kaku sees reasons for optimism in the latest data. Young people around the world express unprecedented interest in space careers. Private investment in space technologies has exploded, with companies developing everything from reusable rockets to space hotels. International space cooperation has survived political tensions on Earth, with the International Space Station remaining a symbol of what humanity can achieve when we work together. Yet challenges remain beyond the technical obstacles NASA's research reveals. Climate change demands immediate attention and resources. Political polarization threatens the consensus needed for long-term projects, and the gap between spacefaring nations and the rest of humanity raises questions about equity and access to space resources. The species that emerged from Africa millennia ago and spread across every continent now stands at the threshold of leaving our planet not just for brief visits, but potentially forever. The latest findings from NASA illuminate both the path forward and the obstacles blocking it. Whether we successfully navigate those challenges depends not on physics or engineering, but on collective human choice. Will we commit the resources and sustained effort needed to overcome the barriers? Will we cooperate across national boundaries to tackle challenges too large for any single nation? Will we maintain enthusiasm and support through the inevitable setbacks and disappointments that characterize any great endeavor? Michio Kaku cannot answer these questions, but his discussions of NASA's work remind us what is at stake. Not just scientific discovery or technological achievement, but the long-term survival and flourishing of the only species we know capable of understanding the universe and deliberately shaping its own future. The road to the stars remains long and difficult, but for the first time in history, we have the knowledge and tools to actually begin the journey. Whether we will choose to do so remains the greatest question of our time.